Of iconic private limited. Mr. Yalla works at the crossroads of artificial intelligence and quantum computing, bringing together theory research and practical implementation. They have been involved with quantum classical hybrid systems, quantum driven optimization, machine learning, and building scalable platforms that make advanced technology more accessible. His contribution stands out because it bridges and connects research with real world applications. A blend that helps demystify quantum computing for many learners and practitioners. We are honored to have him here with us today and hear his perspective directly. Please join me in welcoming Mr. Nyangala.
Good afternoon, everyone. So I can say it's a good evening first of all. Cool. So yes, this is Dr. Jnan, and I really see the faces to learn about quantum and stuff like that. And I've been doing that since the morning session. Okay. So let me put that thing straight and let me ask that thing straight. Um, how many sessions happened from morning to what did you learn about quantum in these two sessions? What is quantum? Emo group. They told us to join hackathon, sorry, join this workshop. That's why we registered. Yes, sir. Okay, interesting. Nice. So, what do you exactly mean by quantum? This is the same question which I asked before sessions asked. What do you mean by quantum? Okay, why do we need quantum? Okay, so that's what we're going to see in today's session, obviously. Because in the upcoming sessions, we'll be moving on to the coding parts and the real life applications of what exactly is quantum and why exactly do we need quantum and all those. So that's why in today's brief session, I will try to ensure that I'm giving some knowledge about quantum through which you can actually understand why do I require quantum at this point of. So yes, first is the same thing which I always like to talk about. First thing is quantum. What exactly is the meaning of quantum? Very simple. Let me start with a basic English example of what exactly do we mean by quantum. Quantum అంటే ఏంటంటే very simple. Small. Okay, quantum is meaning of small. It's a small stuff. That's a simple thing. That's why whenever I talk about quantum space, I'm simply talking about a small space in my known universe. So what exactly do you mean by why? Because I can say that nanoscale is also small. So nanoscale is 10 to the power of minus 9 here. So nanoscale is also small. So what exactly is typically quantum in nature? Simply to put, it's the firm approximate 15. Okay. So when I go to 10 to the power of minus 15 levels, 10 to the power of minus 15 meters weighting, then I will see this something called as quantum. What's so special about this quantum? Where is it? We live in a macroscopic. Okay, the world which we live in, we will simply call it as a macroscopic. Okay, like approximately, consider x meters and square. Okay, we live in a macroscopic world. In this macroscopic world, what will happen? Classical physics applies. So I will call it as some CLS PH1. Some classical physics we apply, the rules of classical physics. What exactly do you mean by classical physics? Very simple. That is my Newtonian plus Einstein. The Newtonian plus Einsteinian physics of the mixture నాకు classical physics అయింది. Okay, in that way, I'll be seeing this classical physics thing. That is car, bike, volcanoes eruption, football, cricket, and the guy slipping and falling down. All these things comes under my classical physics and classical mechanisms. That is in my macroscopic knowledge. But when scientists wanted to study about the structure of atoms or structure of electrons or structure of some subatomic particles, they saw one thing, one difference simply to put. That is, these rules are there, right? Are not being properly applied in here. So simply to put, we are having gravity, something called as gravity. Okay, somehow maybe we have gravity, but it's okay. Let us put the magnetic forces simply to okay. So, but in subatomic world, we won't see the direct magnetic forces, but we'll be seeing the strong attractive force, something like that. Okay, between the quarks inside my subatomic particle, as my protons or neutrons or something. Similarly, the properties what they are behaving or the rules in which they are behaving is completely different from what exactly we are seeing in this universe. That is, in this universe, for example, let us consider you are here. Yes. So let us consider you are here and you're trying to cross a road, and this is a car which is coming to you with a velocity of 100 kilometer per hour. Yes, 100 kilometer per hour. Now, what will happen to this guy? Om Namah Shivaya. Simply to put, he will directly go to heavens. So this will happen in my classical world, simply to. But in quantum world, there is a probability that this guy can escape that. Why? Why? Because simple, the behaviors of my quantum physics. So and that's where the quantum physics came into play, and that's where the scientists got to know that something is different in this quantum area, or something is different in this quantum space, or something. And that's when my entire quantum physics came into play. Simply to put, that's when the entire process of quantum physics came into play. That is, the behavior of subatomic particles is completely different from what I'm actually experiencing in this world. Got it? So that's the first thing. Why exactly do we need quantum? That's what we're going to see next. Now, I hope you guys have understood what we mean by quantum simply to put. Now, same thing again, the quantum physics. What is quantum physics now? You can give an example by yourself, or you can give a definition by yourself. What is quantum physics? Yes, the physics which is applied in my quantum space, or I can say like microscopic space. Okay, classical physics is a physics which I am feeling, I am experiencing at this point of time in this universe. Quantum physics is a type of physics which I will be applying in my quantum space or in a subatomic space or in a microscopic level or whatever it can. Simply to put, for a measure, use 10 to the power of minus 15 meters. Okay, for a measure or for a key or for a stat, just directly use 10 to the power of minus 15 meters. And that's where we are going to see the quantum is coming into. Now, what exactly is different from classical Bitcoin? Very simple. Two fundamentals and derivation of those fundamentals. They are the only difference with my quantum to classical. First one is something called as superposition theory. How many of you know about the superposition theorem? Okay. Second, entanglement concept. So, these two are the ones, or I can say these two are the most primary ones which signifies the important difference, or which gives me the important difference with respect to classical versus quantum. And then from this we can have measurement, the interference, decoherence, all those things are byproducts of this. But most importantly, the two things which mark the difference of classical to quantum is the superposition concept as well as the entanglement concept. Now, what exactly is the superposition concept? Simple. This is position. Let us consider this is position x in this universe, and this is position y in this universe. Okay, and let us consider there is a person here. Okay, or there is a particle called as A. Okay, now let us consider in a real life example. You guys are at this point of time, that is at 4:29 p.m. IST. You guys are sitting in this particular coordinate. At the same time, can you be in some other coordinate in this universe anywhere? Can you guys be there? Like ఇప్పుడు ఆర్కే వ్యాలీలో ఉన్నారు. ఇదే టైంలో can you be there in Chennai? No, you cannot be there, right? It's not possible. ఎందుకంటే because you are here, you are bound to be in this coordinate space and this quantum, right? But when you're dealing with the quantum world, you can be there in the position called as x, as well as the same particle A can also be there in a position called as y at the same time t. That is the concept of superposition, simply to. Okay? That is, at a point of time or at an instance t, an entity can be there in multiple positions, simply to. That means I can be there in X, I can be there in Y, I can be there in Z, and I can be there in any place. Not a problem. Nice for me. Based on what I am defined. Got it? So that's the significant difference between my classical and the quantum. First significant difference. Super question here. Okay? Keep this in mind because we need to have this knowledge when we are talking about why we need quantum. Okay, so all these things we are talking about what is quantum, and then we'll be going to why we need quantum. So for that why stuff, we need this logic. So now there's the first thing about my super question. Now coming to second thing, entire. What exactly is entire? Very simple. You are here at point A. This is so some point A. Sorry, item A at position X. Same position Y, item B. Okay. Now I want to send something to B. I am A. I want to send a piece of information to B. How I am sending? That's completely up my ways. Okay, it can be through phone calls, it can be through WhatsApp, or it can be through mails or whatever. It is. But I want to send a piece of information from my position X to a person called B in Y position. Let us consider we are there in Earth. Let us consider we are there in Earth only. And let us consider this X portion is RK Valley and this Y portion is some Madras or something. In order to send an information or in order to pass an information, what we will be doing casually? Phone call. Okay, we'll simply do a call. Now, here if you say hi, after how much time will this guy receive a hi message in a phone call? Almost instantly. Okay, so I will call the speed as V, but that speed of V is always C, right? It's always lower than C. At most worst case, or I can say scientific science fiction or something equal to C. Okay, what is C? Speed of light. Okay, so the speed at which this information is passing from position X to position Y is at most C. At most ఎప్పుడు ఇన్ఫినైట్ ఎనర్జీ ఉంటే సి అందుకని హైపోథెటికల్ సైన్స్ ఫిక్షన్ అన్నారు అట్ మోస్ట్ ఇట్ ఇస్ సి లేదా ఆల్వేస్ లోవర్ దాన్ సి గాట్ ఇట్ నా and that thing depends clearly on the distance between x and y or the distance between a and b. Okay, now so when I'm saying about RK Valley and Madras, then it's okay, almost instant. But let us consider one another situation. This star is there in Milky Way galaxy. Okay, Milky Way galaxy. GLS. This guy is there in Andromeda galaxy. AD and D, some water, GX, whatever. So now, what will be the time of, or what will be the speed of information travel? Okay, the speed of information travel is the same. Okay, the speed of information travel will be the same. ఇన్ఫర్మేషన్ ఎప్పుడు అదే స్పీడ్ వల్ల ట్రావెల్ అవుతుంది సో దానికి తెలియదు నేను దగ్గర ఉన్నానా దూరంగా ఉన్నానా అని చెప్పి సో లెట్స్ టాక్ అబౌట్ టైం రైట్ సో వెన్ ఐ giving an information from RKV to Madras almost receiving it in an instant manner చాలా ఫాస్ట్ గా రిసీవ్ చేస్తున్నాను నేను now let us consider the point A or the item A is in Milky Way galaxy and the item B is in Andromeda galaxy. At that time, how much time will it take? Sorry, years of light years. Data పేరే light year. So approximately ఎంత 200,000 వేసుకోండి 200 గుర్తులేదు సో ఏదో మొత్తం okay, let us consider 200,000 light years. Okay, from Milky Way to Android. But yes, when I am trying to pass a piece of information from Milky Way galaxy to Andromeda galaxy, I will approximately need a time of 200,000 light years, or let us consider some of 90 years, some X thousand light years for my friend in Andromeda galaxy to have the information. Why? Because the most my information travels at speed of light. At most. So worst if the speed of light will travel out అనుకోను. But still it takes me some X thousand light years from my friend to receive that piece of information. Right? Excuse me. Wait. Okay. So that will be the time span. Because my information travels at most at the speed of now. As per entanglement concept, as per the concept of entanglement, what I can do is that, for example, if A is there and B is there, right? Now, if A and B is there, na, so they are my two persons. Now, I want to send a piece of information. Let us consider A has a qubit and B has a cube. Now, let us consider if these two qubits entangled in nature, if these two qubits are entangled in nature, then I can say that irrespective of distance between them, irrespective of the distance between them, the moment A gives a measurement, the moment A gives a measurement, I can automatically find the value of my B. I can automatically find what is my B. So that is the concept of entanglement. So let me rephrase it or let me put it again for simple clarity. That is, okay, let us consider this one example which I always like to use. tossing of coins. Let us consider you are having two. Okay, మీ దగ్గర two hands ఉన్నాయి కదా. సో ఒక హ్యాండ్ లో ఒక కాయిన్ పెట్టారు అన్నారు. You guys tossed it. After tossing it, you held two coins in your both of your palms. You opened one hand. The answer is heads on. Okay. Now can you say what is the answer in my right hand without opening this particular thing? Can you say that? Can we say that? No, we cannot say that because they are called as mutually independent events. Right? Two coins and a toss చేసినప్పుడు they both are mutually independent. So అప్పుడు నేను ఏం చేస్తున్నా రెండింటికి నాకు అసలు లీకేజ్ లేదు. So when you talk like any type of relation between them, you can find the answer wrong, obviously. Right? So that's what will happen here. Excuse me. Sorry, I'm just having some food. Okay, coming back. So what happens is that you cannot find the answer for the coin in my right by just seeing the answer of the coin in my left. Why? Because both are mutually independent events. Got it? Now, for that reason, what will happen? So, okay, let us compare the same thing with the passing of information. So, phone chaser, later when you send a particular email, the same type of independency will be there at that point of time as because మీ దగ్గర కొంచెం బిట్స్ ఉంటుంది ఐ విల్ బి హ్యావింగ్ సమ్ బిట్స్ సో యాజ్ మై బిట్ అండ్ యువర్ బిట్ ఆర్ కంప్లీట్లీ ఇండిపెండెంట్ ఇన్ నేచర్ యూ కెనాట్ సీ వాట్ ఐమ్ ట్రైంగ్ టు సెండ్ right so for that reason we're having this communication links and all so that I can send my information to you. Well, I can give my information. Why? Because my bits and your bits completely independent in nature. If my bits and your bits are completely independent in nature, then what will happen? By just seeing my own information, you cannot get what is the information of yours is. Okay, or you cannot get what is the information what I am. Why? Because both are mutually independent, right? So for that reason, in order to make you know about my information, what I will be doing, I will simply give my information. ఓకే. సో, ఈ రైట్ హ్యాండ్ కాయిన్ ఆన్సర్ ఏంటి అని నాకు తెలీదు కదా! సో, అప్పుడు నేనేం చేస్తా, ఈ లెఫ్ట్ హ్యాండ్ ఆన్సర్‌నే రైట్ హ్యాండ్‌కి ఇచ్చేసినట్టు లెక్క. ఓకే. లైక్ దట్ ఐ విల్ పాస్ ద ఇన్ఫర్మేషన్. అండ్ దిస్ పాసింగ్ ఆఫ్ ఇన్ఫర్మేషన్ ఈస్ టైమ్ కన్స్యూమింగ్ యాస్ వి saw here. So, this passing of information is time consuming. Why? Because it is being limited by my difference in the costs. For example, I want to send you an information. You are there in Agroveda Galaxy. And then you can't send information fastly. So that's the limitation what I have. Now, what will my entanglement say, sir? Or what will my entanglement is a probability is that? Let us consider two coins. I am tossing the two. But in here, let us consider the two coins are entangled in nature. So left hand coin and right hand coin are entangled in nature. Okay, they are entangled in qubits. Instead of normal coins, they are entangled coins. I toss them, held them in both of my hands. I open the coin of my left hand. I get the answer as yes. Now, instead of opening my right hand, నా రైట్ హ్యాండ్ నేను ఓపెన్ చెయ్యకుండా as well as instead of giving the information of left hand to my right hand, I can find what will be there in my right hand. Okay. So entanglement there are four types. So that is even divided into two types. ఏంటంటే సేమ్ అండ్ డిఫరెంట్ సింప్లీ కన్సిడర్ లైక్ ఒకటే సేమ్ ఎంటాంగిల్మెంట్ ఉందా లేదా డిఫరెంట్ ఎంటాంగిల్మెంట్ ఉంటుంది. సో వాట్ విల్ హ్యాపెన్ ఇన్ ది సేమ్ ఎంటాంగిల్మెంట్ అంటే if my left hand coin gives the answer as chess, I don't need to open my right hand. My right hand coin's answer is also hex. That is the same type of entanglement. And second form is opposite type of entanglement. So in opposite type of entanglement, what happens is that if my left hand coin gives the answer as hex, my right hand coin's answer is tails. Am I opening my right hand? No, I don't need to open my right hand. So I'm going much more actually. I don't need to use that information. But just because these two are entangled in nature, by just observing one guy, or by just observing one piece of information, I can find a piece of information in my second hand, or I can find a piece of information in my second, point or second data, whatever it can. Got it? So that is my entanglement in nature. Now let's go back to communication standpoint at this point. Now, what did I say about communication? So why do we do the communication? Why? Because my thoughts and your thoughts are completely independent in nature. I want you to know my thoughts. If I want you to know my thoughts, what I should do? I should give my thoughts to you, right? Else you can't know what I am thinking. In the book, just because our thoughts are independent in nature, right? So that's the entire reason for this communications and stuff. Now, because of this entanglement nature, what I'm creating, I'm creating a relation between 2 points. Yes or no? Because ఈ రైట్ హ్యాండ్ కాయిన్ ని చూడకుండా instead of opening the right hand coin, I'm finding what is the answer in my right hand. That is, I'm not even considering this guy exists. But still I'm able to find the answer. Why? Why? Because these two are heavily related to each other. The same point I will be using in communication as. What I will be doing, simply to put in a human language, my thoughts and your thoughts will be interconnected so much that whatever I am thinking, you will get to know about it. Do I need to tell you what I'm thinking at that point? Do I need to send you a message or do I need to say anything? Or you will already know about it? You will automatically know about it. How you can know about it? Just because our thoughts are strongly interconnected with each other. As our thoughts are strongly interconnected with each other, what is happening is from me passing you the information, you'll automatically know what I am thinking. So in this process, what is happening? The stress which I'm going through to send the information to you is being reduced, right? Yes or no? Meaning, for example, మీకు వాట్సాప్ మెసేజ్ పెట్టాలనుకుంటా. మొబైల్ డేటా బిల్ కట్టాలా? నా కోసం ఫోన్ ఉండాలా? మీ దగ్గర కూడా ఫోన్ ఉండాలి. మీ దగ్గర కూడా నెట్ ఉండాలా? So, if our thoughts are interconnected with each other, all these resources are not even required, right? Yes or no? The same thing happens in my communication using entanglement nature. So what happens is that I don't need to spend my resources or I don't need to wait for this T time to send the information from A point to B point. Instead, just because I use two qubits which are entangled with each other, whatever information I want B to know, what I will do, I simply put that into my A. When I put that information into A, what will happen? Automatically, my B will know about it. Why? Because they are entangled in A. Understood? So that's concept of entanglement. Simply strong correlation in a way that one guy's actions influence the other guy's. Understood the point? So that is my entanglement nature, simply to put. And Einstein don't like this entanglement nature. Honestly. Why he don't like this entanglement nature, simply to put? Why? Because he says that we know what is E equal to MC square is. Everyone knows the theory of general. No, it's not general. Okay, fine. What? So everyone knows this theory of relativity, but what Einstein is trying to put. Okay, fine, whatever. So that is leave matter like this one. And then C is C matter relation. Then what will happen? If I want to go the speed of light, I need infinite energy. Okay, so infinite, in physics, infinite is a villain. Okay, so whenever infinite comes into play, the meaning is the physicists don't know what's the answer. That's why they simply can answer as infinity. Got it? So that's why whenever you see infinity in a physics problem, consider like this one a problem, like this one where a problem can arise. Because whenever infinity comes, it is the end of discussion. Meaning even the physicists don't know what's the answer. That's why they gave the output as infinity. So same thing comes here as that is this pen is there. I want to throw this pen in at the speed of light. Meaning at that point I should be having infinite energy. Okay, let us consider I am using some supernatural trick to get infinite energy. So what is my utmost speed? Atmost speed is speed of light. So even if I'm getting the infinite energy, I'll be having the little that speed of light more. Got it? So, but here, when I say A and B are entangled with each other, the moment I define A, my B will automatically know what is the answer. That's what I'm trying to say, right? So the moment I define A, my B will know what will be my answer. Now let us consider the same thing. A is in Milky Way galaxy, B is in Andromeda galaxy. This works at the same thing. This works in the same way even when A is in Milky Way galaxy and B is in my Andromeda galaxy. That is, when I find the answer of A, which is there in my Milky Way galaxy, at that moment itself, the answer of B in my Andromeda galaxy will also be different. Okay? How it is possible? Why? Because the distance between A and B is some x thousand light years. Now, if B needs to know that this is my A, it requires x thousand light years, right? Because this information should go and it should reach B before it makes any decision. But if this entanglement comes into play, the moment A is defined, the B will know the answer, irrespective of the distance between. So that's why ancient don't like this. So simply to put, in some way, the information is being passing faster than the speed of light. That's one phenomenon. Second phenomenon is the moment they are entangling each other, they are fixing the information directly. So that's the second probability. But we don't know what is the real thing. So when two things are entangled with each other or entangled with each other, if one guy gives an answer as X, the other guy will also know the answer is X at that particular point of time itself. How it is being happening? Two ways. One way is either this information from A to B is traveling in a way faster than the speed of light. That is one probability. Second probability is during the time of entanglement itself, they will decide that Array Mama answer is extra. Like that, they will decide and then they will start moving away from each other. That's the second problem. But no one knows what is the real answer. If you get to know it, you will get a novel answer. Because no one knows what is the real answer. Like how entanglement is happening. No one knows. Strong correlation with each other, completely all. How the information is going, no one knows. Got it? So these are the two problems. One, the information is traveling at the speed of faster than the speed of light. Number two, during the entanglement time itself, because when I'm entangling two qubits, I need them to stay together to each other. ఆ రెండు పక్క పక్కనే ఉంటాయి అన్నమాట నేను ఎంటాంగిల్మెంట్ చేసేది దూరంగా ఉంటే I cannot entangle the qubits if they are far from each other. I will entangle the qubits only when they are very much close to each other. So in that very much close time, these two qubits will decide on a particular answer. So that is the one more probability of why they are and how they are able to show the same answer. Got it? So this is my entanglement nature. And this is my and the first thing which I explained is a superposition. So these two things are the ones which marks a significant difference between my classical mechanics and quantum mechanics. Okay, classical mechanics na will superposition will happen. Can a superposition will happen in classical mechanics? When this can be there in this position as well as members at the same time? No, it cannot be there. So why? Because we were in classical world. But in quantum world, I can stay here, I can stay in Madras, I can stay in Myanmar, I can stay anywhere at a point of. Got it? So that's my superposition principle. Second thing is entanglement cost. If I want to send a piece of information from one place to another place, I require a time t, okay, which is proportional to the distance. But when I'm talking about entanglement nature, I can strongly correlate two things so can directly send the information without this time constraint. So I can send the information in an instant. Got it? That is my entanglement nature. అర్థమైందా పాయింట్ So that's my superposition and entanglement. Entanglement is nothing but strong correlation in such a way that one guy's answer is enough to find the other guy's answer without me actually calculating the other guy or observing the other guy. Same like the coin what I did. Right hand open చేయకుండానే I can find the answer of my right hand one. Got it? So that's my entanglement nature. Now let's come to the third principle. It's not a principle, it's a byproduct. From now on, we will be seeing the byproducts. First guy is the principle. So second guy is the entanglement. It's a principle. Okay? And this measurement thingy is just a byproduct which we will be seeing. Now let's go to the concept of measurement in quantum. What do you mean by quantum? So what sorry, not quantum. What do you mean by measurement? What is measurement calculating? What is measurement? When do we measure? Two? Goodbye. To find some value from some, like let us consider, I have a class. In that class, I have water. Okay, how much water is there? Or what is the amount of water in that glass? What I will do? I will measure. Okay. So meaning to find the value of some measurement is nothing but what is just to find the value of some. Okay. No. For actually finding the value of something, let's go back to the structure of a qubit. No. Okay, now structure of a qubit, let's consider quantum. Don't get confused with qubit. I'm not talking about qubit here. Let's talk about quantum state. Now, what is this quantum state? Where is what is this? It's a pen. Okay, I am able to hold this pen and I am able to work with it. Meaning, it's a classical phenomenon. It's a phenomenon which I can see in my macroscopic world. This is a classical state. There is a classical state. Okay, meaning it resides in my classical environment and it resides in my classical world. Now, what exactly is a quantum state? Something which resides in my quantum environment or which resides in my quantum space or something. So when I was talking about quantum in the first place, I was mentioning about 10 to the power of minus 15 meters, right? Let's go back to that scale. We'll be having electrons, right? It can be considered as a quantum state. Okay, and we'll be having quarks. These two can be considered as a quantum state. Okay, simply to put, something or anything which resides in my quantum environment. Okay, anything which resides in my quantum environment. If you are getting confused, simply to put, this is a classical state. Why it's a classical state? Why? Because it is residing in my classical environment. Simply to put, I am working with this in a classical environment. Similarly, if anything resides in my quantum-based environment, I call it as a quantum state. Simply to put. Okay. Now, this quantum state will always, not always, but prominently will be in a wave-like form. Okay, that's one another thing to consider. This quantum state will always or mostly be in a wave-like form. How exactly, why exactly it will be in a wave-like format? Simply to put, when I'm talking about a particle, how does a particle look like, or how can I define a particle? I will define a particle like this, or I will define a particle in a 2D plane like this, or in 3D plane in this way. Okay, simply I will. Okay, this only shows. Okay, cool. So in 3D plane, it looks something like this. Okay, meaning I am able to show only one space at that point, or only one position, or one entity, or one environment at that point. When I'm talking about my particle nature. Got it? But whenever I talk about quantum state, na, always or most of the cases, mein, this quantum states will follow the superposition principle. Okay? So what is superposition again? More than one place at a point. Okay? So at the point of time, I can have more than one place. Or I can be there more than one. In order to talk in a systematic or space-based point, I can say that single guy can have more than one states inside. Okay? So for example, simply to put water is there. Okay? Water can be in a liquid form, it can be in vapor form, it can be in solid form as well, right? And at that point, it can be there in three states at the same time. Can you guys tell me what's that point? Okay. So some people might know the answer. It's triple point of. Okay, in this triple point, it's like a temperature scale. So at that point, in temperature, pressure, and everything comes into. So at that point, what happens? My water can stay in solid form, liquid form, as well as vapor form at the same time. Okay, time now we got ice cubes connection, water connection, bubbles for Oscar. Triple point of water. Really, that experiment will you can see in YouTube and stuff. So you can see ice cubes, water, as well as gas also. Three of them will be there at the same time. So that's triple point of water. Okay. This can be achieved at only certain point. Now, let us put this in another way. So in another way, I'll put it as instead of water, I'll keep a quantum state or a quantum particle or something. Okay, instead of water, I will use the word called as quantum particle. A quantum particle can be there in more than one state at a point of time. That is, it can store state 1 information, it can store state 2 information as well as it can have state 3 information as well. And then you can be then here in Madras as well as in Thailand. Okay, so that thing I'll define in quantum as let us consider you are A. A has or A can be there in point A, point B, and point C at the same time. Can I say like that? In that way, I can put it like a quantum state has quantum particle has state 1, state 2, and state 3 at the same point. Okay, or in the same box. So that's my quantum state. Now, if I want to define these multiple states, I cannot use this particle nature because if I'm talking about particle nature, I'm only talking about one set of information here, only one point, or only some square, or only some cube. I'm only talking about one entity. Okay, I'm only talking about just one entity or one space. But I cannot talk about multiple states. So this is my block A. That's it. It's my block A only. So meaning I'm only able to represent one set of information. But a quantum state can have more than one set of information, right? So how can I encode that more than one set of information? By using the waves. So when I'm having waves, I'll be having this type of structure. How many of you remember this? It goes in this way. It goes like sine as well as one more thing, as well as we can have a cos as well. Okay? In a single coordinate space, I can define multiple waves without any, what can I say, correlation or without any, you know, like I can say, congestion or something. A type of problem లేకుండా on the same coordinate space, I can define multiple waves which can run independently to each other, but still I'll be having a space where I'm having multiple waves coming into it. Yes or no? Can you draw it? How does an electromagnetic wave look like? One plane where you can see the electric wave, and one another plane where you can see the magnetic wave. So meaning two different states are residing in a same point. Yes or no? Can you put that in that way? One is electric state and second thing is magnetic state. Two of the states are residing in same plane, right? The same thing which happening in quantum particle as. So in quantum particle, what did I mention right now? More than one state can be there at the same. That's what I meant, right? Now let's put the same electromagnetic wave. Now that electric wave can be considered as one state. That means you are being there in arc energy. And that magnetic wave can be called as other state. That means you are there in Madras also at the same time. Got it? So meaning in a same coordinate space, I can define multiple waves. Got it? So thereby I will say that my coordinate state is always represented in the form of waves. Okay? Will it look like only waves? No. So it will not only look like waves, but mostly we will represent it in the form of waves. Just because to hide to show this super question names wrong. Because a quantum particle can hold more than one state at a point of. So how can I represent that more than one state at a point of time? By simply using this wave. In wave, I can show the electric waves movement as well as the magnetic waves movement as well, right? In the same way, in the same way, I can show the state of one wave or the state of one thing as well as the state of other thing as well as the state of some other thing as well. I can show the states of all the thing at the same. So that's what will happen in my quantum. Got it? Understood, everyone? So what exactly is the quantum state and how it is represented? Now, now let's go back to measurement concept. Yes. Now, so what exactly is measurement? As I already mentioned, calculating something. Calculating this value of something is my measurement. Okay. Now, when I'm measuring a qubit, so not a qubit, when I'm measuring a quantum state, because I did not talk about qubit yet, that's why I'm not saying about qubit. But I will say about it in some time. Now, when I'm measuring a quantum state, what will happen? Very simple. That wave will be decomposed into a particle. Particle में can I store multiple sets of information? It's a question. Like in particle, can I store multiple states of information? Yes or no? It's a no. Yes, it's a no. Okay. So I cannot store multiple pieces of information in a particle. That's why I told you to, and that's why I explained about this wave nature, having electric state, magnetic state, and everything. Right? Why? Because if I want to store multiple sets of information, I can only do that by using waves. By using a single particle, I cannot store or I cannot represent multiple states of information. Got it? Please keep that one thing in your minds. That is, by using points or by using particles, I cannot store or I cannot represent multiple states of information. Okay? Ice cube point. Ice cube ni water ni ఒకేలాగా చూపించగలుగుతారా? Or let us say this is a pen, right? I want it to look like red as well. Can I do that? I cannot do that. Pen is a pen because it's a particle. Okay? The particle will only be a particle. Okay? So అది only ఒక state ని మాత్రమే capture చేయగలుగుతుంది. I cannot capture multiple states in a particle. But in a wave, I can do that. In a wave, I can capture multiple.